So if we look at this, what we have is an association between the number of times that someone has solved a Rubik's Cube and the time it takes for them to solve it. We don't see a scatter plot for this, but it does tell us that there is a r squared of 54%. So 54% of the variation in time is explained by the model. If the standard deviation for the number of times solving a Rubik's Cube is 138, and the standard deviation for the time it takes to solve is 24 seconds, what is the slope of the regression equation? Okay, so there's a couple of things that you could mess up on here that would throw off your answer. And then, if you got both of these right, then you're good to go. Otherwise, it could be just a random guess, and hopefully you're not doing that. Okay, so the first thing we want to figure out is, okay, if I've got an r squared, then I want to square root that. So I'm going to take the square root of 0.54, and I hope everyone was able to do that, to get 0.735. And I'm going to call that good for right now, because now the next thing we want to do is we want to do remember that we're going to use our slope equation. So that's r times the standard deviation of y over the standard deviation of x. So I want to take this and I want to plug it in for my correlation. But before I do that, I want to kind of think through this a little bit more. And I want to think, okay, what's being correlated? We've got the number of times someone solves a Rubik's Cube and the time it takes for them to solve it. So there's no other clues in here except kind of knowing what the two variables are and kind of figuring out, should this be a positive or a negative correlation? So just intuitively, if you see that someone has solved this, more often, would you expect them to solve it faster or slower?
Faster.
Faster. So if it's faster, the more often you solve it, then the time should be going down. So if one variable goes down as the other goes up, then that is showing it's going to be a negative correlation. Okay, so now, as long as you have a negative correlation, then you know that it has to be a negative slope because your standard deviations are always positive. So the only thing that can turn your slope negative is by having a negative correlation. So I'm going to cross off these two. I will say that C was the most common wrong answer, but we'll see why, and that's a quote a best bad answer sort of thing in this problem. So anyways, I'll plug this in. Negative 0.735 is the correlation. And now I need to figure out the standard deviation of y and x. So here's where I need to kind of go through and figure out, well, which one's my y and which one's my x? There are a few clues given in here, and some of it's just going to be like your own intuition. So what would we probably use to explain the other? What would probably be the response? So in my head, the number of times that you've solved a Rubik's Cube is probably going to explain how long it takes for you to solve it. So in my head, just intuitively, I would put the number of times right here for the x and the time it takes for the y. So, I think it's helpful to kind of imagine how you'd set up the scatter plot when you read a problem like this, because that can tell you, okay, this is my x, this is my y, this is my explanatory, that's my response. Now I know which one is my y standard deviation. Another clue in here is that it says in the second sentence, the derived model explains 50% of the variation in time to solve a Rubik's Cube. Well, we're always explaining the variation in your y value. So this is telling us right here that it's the time to solve is our y value. Okay, so we have a good model set up right here. So that means my standard deviation of y needs to be the standard deviation of the time, and that is 24 seconds. So right here, I'm going to put 24 for the standard deviation of y. For that means the standard deviation of my x is going to be the 138. So when we go through and plug this in, it should end up being negative 0.128. Unless I made a mistake with calculations. I'm going to set this up. But that's, the only one that with both of those things makes sense. And so the two things where you could go wrong is not showing that this is a negative correlation. So that's the first place you can make a mistake. And the second place is by flipping which is your X and your Y standard deviation. And so either of A and C are kind of your best bad answers, but still, you know, negative 0.128 is correct. All right, so that's all well and good. Any questions on that? Okay, so now we are looking at chapter 9 today. And some of this, if you read it, this is just gonna kind of be going over some of the stuff we did last night. And kind of, some of this is a little bit tricky. Maybe it's just me, the way my brain works, but I'm gonna assume some of you are struggling with some of these ideas. So we'll go into more detail on some of this, but hopefully a lot of it's pretty straightforward. Subsets in large data sets. So within a single data set, you might actually have different populations that are kind of mixed that can result in two different trends going on. Now, sometimes we don't know it from the beginning. And now I'll tell you, these three come from three different data sets, but we're going to pretend like this is all one thing going on. So in this hypothetical example, let's say that we had a scatter plot. Now, we would probably not, well, we would definitely not see a residual histogram that looks like this. But remember, if these were our residuals, and I'll move this out of the way so we can actually see the numbers at the bottom, then we might see, you know, if there's like a cluster below with negative residuals and a cluster above with positive residuals, maybe what's going on is that we actually have two different populations represented. Now, this is kind of an extreme example, and it wouldn't appear exactly like this, but really the whole purpose of knowing this is just to, you know, conceptually be able to interpret what's happening if we saw things like this going on. So bimodal or multimodal residual histograms is going to be a clue that there's maybe subpopulation subsets that should be, you know, separated. So that's helpful. And, you know, sometimes we know it ahead of time. So I'm going to bring up another example. This one's from your textbook. Sometimes it's not so much that we discovered after the fact that there's a different subgroup, but sometimes we code things ahead of time to be different. Like there's an example in your textbook about cereals and the sugar content of them. So in this case, we have the bottom shelf and the middle shelf of the aisle, the cereal aisle, both kind of trend together. But if you look at the top shelf, you can see that this is a very different regression model. So maybe this one should be excluded from the overall population, and we can show this separately, just to say, hey, there's a very different sort of trend going on here with these types of cereals. Now, that we noticed that because it was coded ahead of time, and we saw three different subgroups. So again, the important thing is the analysis and the interpretation of it, and showing that maybe this subgroup should be pulled out from the overall regression and just presented separately. Okay, so you're not going to have to code stuff like this on your own. I mean, this would take a lot of time, and you don't have time on the AP test to do this. So it's always going to be interpretation questions with stuff like this. Okay, so now we come to extrapolation. And regression models, like we've been using, they are used for prediction, but the most appropriate use for a regression model is to predict something that comes within the range of the original data. So if your data goes from 0 to 100 and you wanted to predict what would happen at 40 for an input as your explanatory variable, that would work. And that's called interpolation. So you might have heard that word. And interpolation is different from extrapolation, which is whenever we extend this regression model beyond the range of the data. And what happens then is the uncertainty of other factors can overwhelm the model, and our projections are usually unreliable. And I say usually, we'll talk about that in a second. So this is extrapolation, and it should be avoided with a caveat, if you extrapolate just slightly, like again, imagine we have some explanatory variable that goes from 0 to 100, and we want to predict what would happen at 105. That's not the end of the world because we're only slightly extending it. It is technically extrapolation, but that is far more acceptable than, you know, going from 0 to 100 and predicting what would happen at 1000 for our explanatory. So that would be major extrapolation and definitely wouldn't be reliable. Okay. So this is just kind of showing what happens here. So you can see this is, as this grows, and this is, I don't actually even know what this measure is right here on the left, but what's happening is as this goes along, the uncertainty is increasing. All right, so by the time we get to the end, you know, just with this uncertainty model, it could be up here, it could be down there, it could be right where it's predicted. More uncertainty is introduced, and the actual word for this is skedasticity. That is not something you need to know unless you're going to study more stats in college, and you'll learn all about that there. So hetero means that the variance here is changing and getting wider and wider. If it was homoskedastic, then it would kind of stay the same throughout. All right. Brief little aside with that terminology. That is not something you need to have memorized, which is why you haven't seen it yet. Okay. Extrapolation. So this is an example again from the textbook. A problem with it, like we talked about it conceptually, but you can see here, these were gas prices going from 1980, and this is price per barrel of oil, 1980 down to 1998 or so. I don't know when that stops. And you can see what's going on is that the gas prices just seem to be going down. So you can make some projections of what would happen from there. And I actually remember driving around in the mid 90s on road trips and seeing gas prices below $1. So like 90 cents for gas. Well, that didn't last for very long because here's what actually happened. Here were some projections of where the gas prices would go. Well, what happened, you can see the same data right here goes this kind of steep drop at the end, which is, you can see right here. Well, and then it spiked up. So by the year 2007 or so, we're up to over $100 per barrel of gas. And you might be, remember seeing like $4 per gallon of gas at the pump. So yeah, these projections were meaningless. And a lot of times with commodities, you can't project very well. And even since then, the trend has been downward. I don't know where it's at, but especially with the pandemic, it's gone down from there. Everyone thought, oh my gosh, it's just going to keep going up to $200 per barrel. So that, I think, serves the purpose of reinforcing that point. Okay, just another example of this. This is kind of more two-dimensional, or showing it in a different way. This is called a cone of uncertainty. And this is specifically showing the cone of uncertainty that we had for Hurricane Katrina back in 2005. And you can see as it got further away from the actual location at the time, there's less certainty on where it's going to end up. But this is also showing how that cone of uncertainty has improved in the last 10 years or 15 years. It's probably even gotten better. So you can see what the cone of uncertainty would be. But you can see they were projecting a wide area that could potentially be hit. Okay. And here's just a different example of extrapolation gone wrong. And I put a few cartoons up on the Canvas page, which, you know, they're nerd funny. They fall in that category. So you might enjoy it. But there you go. So be prepared. If you're alive in 2109, you're just gonna be saying sustainable for every single word. Kind of, if you've read what is it, 1984, if you're familiar with Newspeak, there you go, be something like that. So anyways, this is the part of the chapter that is a little bit more confusing. We've got outliers, leverage, and influence. And the reason they're confusing, at least for me, and I'm speaking from my own perspective, is not so much that individually they're confusing topics, it's that, you know, knowing the difference between a point that has high leverage or an outlier or has influence, it's just kind of confusing. It's like, it's almost three ways of saying the same thing, but there is a difference, and that's what we're going to talk about. So we will go into all those. We're actually going to start a little bit out of order. We're going to start with leverage. And what we have here is our basic understanding of leverage. It's actually hopefully pretty easy to understand. It's okay, a point has leverage if its x value is far to the right or left of the main clustering of data. So in this example right here, we do have a high leverage point because this point right here has a pretty big gap between it and the rest of the data. So the name leverage itself will hopefully give you a clue. So remember, levers, and you've learned this to some degree. If you are taking physics, then you're going to be more familiar with this. If you're trying to move a big weight, all right, and you want to move it, you can move it with a lever. It's a simple machine. And, you know, if you have a lever, that's great, but this is going to still be pretty hard to kind of push down on that lever, lift it up. So if you extend your lever out really far, and then you pull down there, then what you're doing is you're decreasing the work and forces required to move that big weight. So notice that we have higher leverage the further away and the further out we make that. So that's kind of the idea. If you can kind of think of this point right here as a lever, so that is going to have more impact based on whether it's in line with the trend or not in line with the trend than any other point in this data set might. Okay, so hopefully that's a helpful analogy. So keeping in mind that a point can have high leverage without changing the model, or you need to keep in mind that a point can have high leverage without changing the model like above. So the trend line right here is basically like that, and it's high leverage right here, but it's not actually changing our model. If this point didn't exist, our trend line would still be going about right there. Now this one to the right is not high leverage. Its x value is not separated from the main clustering of data. So here's the main cluster of data, and this is falling right in the midst of it. So no leverage there. It is an outlier. It could affect the model. So we'll talk about whether it will affect the model or not. Okay. So an important thing to know about leverage is that even if it doesn't change the model, it will change the correlation. So we had this regression line, and then we added this other point, and it reinforced our regression line. It might have changed it very slightly. But what it did change is the correlation. Now this is going to be a much stronger correlation. Well, maybe not much stronger. This is already pretty strong. You can see that clustering of data. So I'd guess that's already over 0.9 correlation, but this is going to be even bigger. So we might have gone from like 0.95, add this other point in, now we're at 0.99, right? So leverage will increase our correlation coefficient if it's in line with the trend. And therefore, it's also going to change our coefficient of determination, R squared. But it's not going to change the model. Okay, hopefully clear enough. So now we have outliers. And here's kind of the frustrating part with this, because you have to be a little bit hesitant if you go online to get some extra help and go other places and learn more about outliers. People can define outliers differently. But this is the AP definition. And so this is the one that we're going to care about. An outlier in a regression is a point that does not follow the general trend shown in the rest of the data and will have a large residual when the least squares regression line is calculated. So according to this definition, I would say this red point is not an outlier. So it is in the general trend. Like we were talking about before, that trend line was already right there. This is not out of line with it, so it's not an outlier, even though it's really far away. So maybe a way of thinking about this is that they are values that are far above or below the main clustering of data in the y direction. So if we added another point right here, of course we'd recognize that as an outlier. And the main thing that distinguishes that from high leverage is that we're talking about a big difference from where we would predict it would be. Okay, we'll kind of summarize this again. But on this one, hopefully you've understood kind of the distinctions there. So anyone can do this. Go ahead and annotate and identify any outliers in this diagram. Okay. And of course, more people, if you guys agree that those are the outliers, then I agree as well. So outliers, what about high leverage points? Okay. And very good. So these are, like you showed, those are outliers, but they're not high leverage. So if you were showing those as having high leverage, that's not correct. That's okay though. So those are outliers up at the top. This right here, like you guys are showing, that's our only high leverage point. Okay. And we'll look at some actual numbers and kind of see using actual data, kind of what it means, whether something's in, well, I'm jumping ahead of myself. We'll look at some more examples, I'll just say that. So leverage and outliers, this is kind of to summarize these things. If a point has leverage if it is separated from the data in the X direction. A point is an outlier if it's separated from the trend line in the Y direction. And it's important to say the trend line and not the least squares regression line, because if we got our correlation, we might have a trend of the data with an outlier right here. So our trend line, not the actual line that we calculate, but the one that we see right here, this one's way out of line with it. So that is an outlier. All right, probably pretty obvious. I didn't need to say that, but it's worth saying maybe. Okay, a point can be an outlier and not have high leverage. Okay, and the way this can happen is, let's pretend that we have, sorry, we've already talked about that. I was jumping ahead of myself again. But yeah, if we got the correlation right here, an outlier without high leverage, we've already seen that. If you have an outlier with high leverage, it's going to have an even bigger impact on the regression model than if it was just an outlier alone. Okay. So I've been jumping ahead quite a bit, so now let's actually move ahead so I can try and say those things. An influential point is one that actually changes the regression model significantly if it's removed. So an outlier is often influential. This is what I was about to say a minute ago. An outlier can actually have its impact mitigated or even negated to a large degree if you have so many data points that the outlier doesn't really have enough weight. So if I've got a correlation, I'm going to try and draw a lot of dots here. Imagine I've got hundreds, maybe even thousands, I don't know, of dots. And then I've got an outlier right there. There's going to be so much in the calculation that we do, there's going to be so much weight with this mass of data right here that one outlier, even a few outliers, might not have enough power, influence to actually change our regression line significantly. So that's one thing to keep in mind. Now, if it was only a few points and we had that outlier, then it would most certainly be influential. That would change our regression line. A high leverage point is sometimes influential, and again, that depends on if it's also an outlier. If it falls in line with the scatter plot trend, it's not influential, but it does change the correlation coefficient. So just to make sure it's really clear, if I have a cluster of data like that with a trend line, this point would be high leverage that's not influential. This would be high leverage that is influential. Okay, so hopefully that distinction is clear enough. Okay, and now we're looking at some actual numbers, and we can see a few different examples. This is our original data. You can see the actual coefficients. I should point out they're using ax plus b instead of what we use, which is a plus bx. So that just means the slope and the y-intercept have flipped. Okay, but besides that, we're just comparing the numbers one to the next to see if there's a big change. We add an outlier right here. Well, does that change our regression line a great deal? Well, not really. I mean, the numbers aren't the same, but I wouldn't say that was a big change. So I would say that this is an outlier that's not influential and it doesn't have leverage. Okay, the next one, we've got this point right here added to the data set. Now you can see, I don't even need to compare the numbers, though you can. You can see the regression line now. This is a line that's got leverage. Sorry, this point has leverage. It's an outlier, and it therefore is influential. So if it's an outlier and it's high leverage, it will be influential. There's no doubt about it. The next one, we've got this point. We've seen this already, so we can just show real quick. This is high leverage, but it's not very different from what we'd expect. So it's low influence, or not influential, not an outlier, but it is high leverage. And then the last one right here, low leverage or even no leverage. It is an outlier, and this one I would say is influential. There's no clear-cut line that says, okay, this one now is influential, it's changed it enough. So you just kind of use your own judgment. But I would say when you compare the slope right here to the original, you know, we changed that by a pretty good factor. So I think it's fair to say that one's influential. Okay, so hopefully that's helpful seeing that. And so what we're going to do with this right here, and I'm going to need one of you to volunteer, but we're looking to add a point to this scatter plot that's an outlier, that's influential, and is high leverage. All right, so let's see if that point meets all three criteria. So here's the trend line. Is this high leverage? I would say that it's high leverage. Is it an outlier? Is it far from what we'd expect? Well, there's really no difference from what we'd expect. So here it's not actually an outlier. That's okay. Maybe what's a point that's high leverage that's an outlier? Okay, so now we got this point. Again, here's the trend line before that was added. So definitely high leverage. From what we would predict before it was added, yeah, that's not where we'd expect it to be. So it's an outlier, it's high leverage, and therefore it's going to be influential. In fact, with a data set like this, it's going to be very influential. So that one works right there. Okay, let's look at the next one. Outlier, influential, low leverage. Any thoughts on where that point could be? All right, so let's see. Here's our trend line. Low leverage, because while it is separated, it's not majorly separated. So yeah, I think it's low leverage. An outlier. This is probably right at the edge of what we'd call an outlier, but I think that qualifies. And therefore it's influential. Yeah, this is going to pull our regression line maybe more like this. So I think it's fair to say that that works. Something that would have even more influence is low leverage. If we added this point, we just dropped it down even further. So we've got low leverage still, but even more of an outlier, which would make it even more influential. Okay, the next one I'm gonna, well, yeah, let's talk about this one. An outlier with no leverage. It doesn't say anything about influence, but an outlier with no leverage. All right. So remember, leverage is your distance from the main clustering of data over. So we're looking for something with no leverage, and we've got a high leverage point right here. All right, so I've got a few points added kind of in this vicinity right here. And I think those work. Those are definitely outliers. No leverage because they're really within our main clustering of data, within this range. So no leverage is not left or right, but yeah, definitely outliers. So that's a good range. Anything put in this range right here or up here. Okay, let's look at the next one. Not an outlier, not influential, low leverage. I'm not quite sure I saw where that point showed up at. Anyone else want to add a point on there to show something that's not an outlier, not influential, and with low leverage? Okay, I like that. Okay, those are both good points. I was going to say, but you guys added the points already. I was going to say, here's the trend line just to kind of help you think of it. Both of these work. Not high leverage right here, or with this one, but and neither of them are outliers. They're both pretty well in line with the trend line, and they're not influential because they're just basically they're not going to change our regression model. So last one right here, not an outlier, not influential, but very high leverage. There it is. And again, you could we keep going up to the top and to the right, and that's kind of makes the most intuitive sense here. We could also put a point way down here. That's high leverage. Remember, high leverage is just the distance away. I keep repeating that, but it's worth hearing. So those are both really far away in the x direction, so they both have high leverage. But if our trend line was already going like this, then neither one of those are outliers, and so they're not going to be influential. Okay. So again, sometimes if you go to other sources, and this is the way I'm teaching it, I think this is the right way the AP is expecting. Some people kind of have different ways of identifying outliers. And I would not call this one an outlier, but other places you go might still call that one an outlier. But I think according to AP, it's not. So just be careful if you're looking at other sources online. But anyways, hopefully all this is making sense, and you can get more practice. Part of the homework tonight has questions in a similar vein to this. All right, this is actually from chapter 7. It's something I skipped over. And what we have is a correlation table. And you might have even, I don't know if you've ever seen anything like this, like that you had to interpret, but you have 9 different factors right here, variables, and you have the same 9 variables right here. So when you have this variable correlated to itself, it's going to be 1.00 correlation. And you can see along the diagonal, that's what we have. But then everything gets correlated to every other variable. The problem with correlation tables, and if you read chapter 7, you already saw this, is without seeing the actual scatter plots, they're kind of meaningless. So this 0.95, I'll just pick that one. That 0.95 sure looks great, but if it's a curved, if there's a slight curve to it, it's nonlinear, that 0.95 means nothing. So you just have to be careful with correlation tables. Sometimes if it's like a question and this is all they give you, they might put in an assumption that says, assume that all correlation requirements are met, correlation assumptions are met. And then you can say, okay, fine, it's linear, so let's move forward. All right, this is the one that is a little bit weird at first, but I don't think it's overly complicated. So you should not use summary statistics in lieu of the original data when you're creating your scatter plot and performing your regression analysis. And the big reason why is that summary statistics are going to artificially inflate the correlation and give a false impression of the explanatory effects in the model. All right, that's a bunch of words. Let's see practically what's happening here. So this is an example from the textbook. And what we have on the left is the original data, and then we have the summary data. And notice that our R squared on the left is 41.5%. So, I mean, that might be good. That might be kind of useless. You know, it depends on what you're going for. On the right, our R squared has jumped up to 80.1%. So just to explain what's happening when we talk about using summary statistics, for this height, I think this is 61 inches right here. Those three people that were 61 inches tall had their weights averaged. So this point, this 1 point is replacing those three people. If we come over to 64 inches, however many people that is, like 6 people, have all been averaged and replaced with 1 point. And the more often you do this, even here we have this outlier. But when we look at the average for that, you know, it's only a little bit above the regression line. So by averaging all these people into one data point, we are artificially inflating the correlation and the explanatory effects of this. So I mean, right here, we've improved the power by almost double, but we manipulated the data to do that. So it's not a very accurate picture. So if summary statistics are all you have, of course, work with them. But if you have the option to work with the raw data, you always want to do that with scatter plots. Hopefully this is all well and good. Any questions on this stuff? Okay. So the last little bit, we're going to go through one problem and then we will be able to wrap it up for today. We'll hopefully be able to do this somewhat quickly. Okay, so this is from the textbook. If you don't need to open your textbook because I've got everything you need to see right here on screen. But what we've got is, for some reason, people like to swim across Lake Ontario. I can't imagine why. But 42 times people have done it between 1974 and 2006. And we're interested to figure out whether they're getting faster or slower at it. And you can see there was a regression that was performed, the crossing against the year, and the what we see here is just the residual plot. So we're not seeing the original scatter plot. And we'll kind of talk through this more. But what does R squared mean for this regression? Okay, well, R squared, 1.3%. I think this is what you would call a useless model if your R squared is only 1.3%. So before we can kind of interpret this 1.3%, we need to know what is being predicted based on what. So it says that there's a regression between the time that it took against the year. So I think it's only logical to put the year as your explanatory variable and the time as your y. Again, I think it's always helpful to actually draw out a little scatter plot to help you understand kind of what's going on. So R squared explains the variance in your y variable, in your response variable. So 1.3% of the variation in time to, and I'm going to put ... time to swim across Lake Ontario is explained by the model. Okay, so we just explained with context what that r squared means. So hopefully you can paint kind of a mental picture of what's going on with the scatter plot. And my guess is it's going to look something like this. All right, so basically no correlation. And with a 1.3 r squared, I think it's safe to say we're going to see something like that. But anyways, for a lot of these, we're going to pretend that this model is useful. Are the swimmers getting faster or slower? And explain that. Now, I might not write this down on the screen, but we can kind of talk through it. So I wanted to show this one because it also gives us this computer printout. A lot of you will end up taking a statistics course in college, whether a more advanced one or one specifically for your major, and you're going to be working with statistical software. There's stuff called like SPSS, SAS, R, all kinds of different things. And the bottom line is you will frequently see a printout that looks like this, and you'll need to interpret it. So it's good to learn about it. We talked about it already. The intercept right here. Well, that's specifically referring to your y-intercept. Somehow everything just got deleted, but whatever. So your y-intercept is right there. That means this right here, that 5.14 is the slope. So we kind of figure out our slope through deduction. We identify the intercept first, and then it's like, okay, if that's the intercept, then the other one must be the slope. Okay, we already talked about that. So are the swimmers getting faster or slower? Well, if our slope is positive, that means for every year that we go up, we're adding 5.14 minutes to the time, which means we're getting slower. So we would want to write something to that effect. Swimmers appear to be getting slower because for every year, we're adding 5 minutes to their expected time, and there you go. Okay, so the last one here, again, we'll just kind of talk through it, but it says this outlier point, and hopefully when you looked at the residuals, that stuck out to you. That outlier was back in 1987 when this lady swam a round trip across Ontario. So she's especially crazy. Clearly this swim doesn't belong with the others. Would removing it change the model a lot? And here's where I want you guys to maybe throw in your perspective. Would that change our model a lot or not very much? No one's feeling especially confident in how they'd interpret this. So another way to think about it is, would these parameters for our regression model, would they change? Or would they change a great deal? Do you think it'd still be pretty close to 5.14 for the slope and negative 9,000 for the intercept?
I think they'd change a little bit, but not much.
Okay. I think it's fair. I think that's a fair answer. And that's kind of where I would be leaning as well. As long as you can back this up statistically, there's a lot of answers you could give. So just to give an example of, no, this wouldn't change it, you could say, while this point is an outlier, there are enough other data points clustering around the regression line that it probably is not influential. And so it wouldn't change our regression equation very much. So I didn't write that down, and that's a lot to write, but I just want to save on time. Now, if you think it would change it, you could argue your point. You could say, this outlier point, I believe, would be influential and change the regression equation because it is so far removed from the rest of the clustering of the data, it would move the regression line a significant amount. And so therefore, yeah, it's influential. So, I mean, if I saw either one of those responses and I was grading this, I'd say use some really valid statistical understanding to justify what you thought. Personally, I think it's not. So what you said, I agree with. Okay. Exercise 26. So now we're jumping to 28. We'll do this a little faster now. What happened is this outlier was removed and they reran the correlation, the regression analysis, came up with this. And you can decide if that was a big change or not. It went from 5.14 to 6.17, from negative 9,000 to negative 11,000. That might be a big change to you, it might not. All right, so if we look at this, in this new model, the value of the standard deviation of our residuals is much smaller. What does this mean in context? Okay, so I didn't point this out before, but this S right here is your standard deviation of your residuals. And this is our standard deviation now. Now notice it's 443 and 293, basically, 444. So that makes a lot of sense if we're talking about swimming across across Lake Ontario. That's big time. So 444 minute difference isn't unheard of for a standard deviation. So let's kind of look at this. How would we interpret this one? We would say the average difference between an actual swim time and its predicted time is 292.6 minutes. And they asked for kind of a comparison. So, I mean, it seems that they're asking for a comparison. So I'd say which is much smaller than the original model. And here I can put the number, 443.8 minutes. So I did write that one out, and we've interpreted it. We've put some context. We've shown that we know what that number means in context. These kinds of questions are just making sure that we're not just looking at numbers, plugging them into a calculator and saying, there's your answer. Okay, now would you be willing to say that the Lake Ontario swimmers are getting faster or slower? Now, according to the model, they're getting slower, but this is where it comes back to this. Even without that outlier, we've got a 4.1% R squared. Would you say that this model is useful at all?
No.
No. So here's where I wouldn't say anything is accurate about this. In some ways, we approached it as though it was accurate, but here, when we really get down to it, it's useless. Okay, so that's kind of where you'd speak to that. I did add one other question here. It's worth talking about this. Let's pretend that this was a useful model, okay, for this question. Imagine someone swam a distance in 1,075 minutes in 1980, while another swam it in 1,150 minutes in 2000. Whose achievement was more remarkable, statistically speaking? Now, without statistics, we'd say, oh, well, this person swam it faster. But what we're doing, this almost seems like a z-score question, but we don't know the mean and the standard deviation. So instead, we need to approach this a different way. So what I want to do is I want to figure out what predicted time would it take in 1980. So I'm going to predict the time in 1980. I shouldn't put it that way because I'm not predicting the year. I'm going to predict the time in 1980. And that's going to be, let's see, my coefficients, it's a plus bx, so my intercept is negative 11,048.7. I got that right here. Plus 6.1, I'll just abbreviate it to 171 times the year. So I need to figure out what value would we predict in 1980. Well, we can plug those numbers in. So go ahead and do that. And we'll also predict for 2000 because that's the other value. So and as soon as someone has an answer, you can go and write that in for me. The predicted time in 1980 and the predicted time in 2000. And just to make it easier, you could round it to the nearest minute. Okay. So that's how long we would expect someone to swim it, pretending this is a useful model in 1980. And in 2000, how long would it take? Okay, there we go. 1,293 minutes in 2000. Okay, so if we're trying to figure out whose achievement was more remarkable, then with a scatter plot, what we're talking about is whose residual is greater, or that's one way of thinking about it. So we'll talk about residuals more tomorrow because some of it I just kind of skipped over, but we'll come back to all this. So residual is your actual minus the predicted. So let's figure out the residual for 1980. We know how long it took this person to swim it. So figure out the residual in 1980 and the residual in 2000. And again, as soon as you guys have calculated that, you can put the number up there. Okay, so we got a negative 143. One thing right here, that 95 is correct. Make sure, because it's the actual minus the predicted, it's actually a negative 95. So, but anyways, we've got that. So now we can just kind of compare this and say, in 1980, this person only swam 95 minutes faster than we would have expected. This person swam it over 2 hours faster than we would have expected. So in that sense, the 2000 time was more impressive. Again, this is only really useful if the model itself is useful. So we're pretending that it is and that it's not completely worthless. Okay, but hopefully that idea makes sense. So that's what we're doing for today. And I'll just show the homework. And didn't say it before, but if you haven't been paying attention, we're over 200 pages done with the textbook now. So congratulations. Now, the homework here, tomorrow, nothing special to say, but it's just gonna be just random minutia that I've forgotten to cover that we just need to go over with more time. That'll be tomorrow. So if you have specific questions, we can talk about that a little more. But besides that, that's all I have for you today. If you have questions, you can stick around, but we were able to finish it right at an hour. So not too bad for today.